In the last video, we started with a star in its main sequence, like the sun. And inside the core of that star, you had hydrogen fusion going on. So that is hydrogen fusion. And then outside of the core, you just had hydrogen. You just had hydrogen plasma. And when we say plasma, it's the electrons and protons of the individual atoms have been disassociated because the temperatures and pressures are so high. So they're really just kind of, it's like the soup of electrons and protons as opposed to proper atoms that we associate with at lower temperatures. So this is a main sequence star right over here. This is a main sequence star right over here. And we saw in the last video that this hydrogen is fusing into helium. So we start having more and more helium here. And as we have more and more helium, the core becomes more and more dense because helium is a more massive atom. It is able to pack more mass in a smaller volume. So this gets more and more dense. So core becomes more dense until at some point, and so while the core is becoming more and more dense, that actually makes the fusion happen faster and faster because it's more dense, more gravitational pressure, more mass wanting to get to it, more pressure on the hydrogen that's fusing, so it starts to fuse hotter. So let me write this. So the fusion, so hydrogen fuses faster. And actually, we even see this in our sun. Our sun today is brighter and hotter. It's fusing faster than it was when it was born 4.5 or 4.6 billion years ago. But eventually, you're going to get the point so that the core, you only have helium. You only have helium. So there's going to be some point where the entire core is all helium. And it's going to be way denser than this core over here. All of that mass over there has now been turned into helium. Not all of it. A lot of it has been turned into energy. But most of it is now in helium. And it's going to be in a much, much smaller volume. And the whole time, the temperature is increasing. The fusion is getting faster and faster. And now that it's in this dense volume of helium that's not fusing, you do have, and we saw this in this video, a shell around it of hydrogen that is fusing. So this right here is hydrogen fusion going on. And then this over here is just hydrogen plasma. Now, the unintuitive thing, or at least this was unintuitive to me at first, is the stuff that's what's going on in the core is that the core is getting more and more dense. It's fusing at a faster rate. And so it's getting hotter and hotter. So the core is hotter, fusing faster, getting more and more dense. I kind of imagine it's starting to collapse. Every time it collapses, it's getting hotter and more dense. But at the same time that's happening, the star itself is getting bigger. The star itself is getting bigger. And this is actually not drawn to scale. Red giants are much, much larger than main sequence stars. But the whole time that this is getting more dense, the rest of the stars, you can kind of view it as getting less dense. And that's because this is generating so much energy that it's able to more than offset, or better offset, the gravitational pull into it. So even though this is hotter, it's able to disperse the rest of the material in the sun over a larger volume. And so that volume is so big that the surface, and we saw this in the last video, the surface of the red giant is actually cooler. Let me write that a little neater. Is actually cooler than the surface of a main sequence star. This right here is hotter. And just to put things in perspective, when the sun becomes a red giant, and it will become a red giant, its diameter will be 100 times the diameter that it is today. Or another way to put it, it will have the same diameter as the Earth's orbit around the current sun. Or another way to view it is where we are right now will be on the surface or near the surface or maybe even inside of that future sun. Or another way to put it, when the sun becomes a red giant, the Earth's going to be not even a speck out here, and it will be liquefied and vaporized at that point in time. So this is super, super huge. And we've even thought about it. Just for light to reach the current sun to our point in orbit, it takes 8 minutes. So that's how big one of these stars are. To get from the one side of the star to another side of the star, it'll take 16 minutes for light. for light to travel if it was traveling that diameter, and even slightly longer if it was to travel it go in a circumference. So these are huge, huge, huge stars, and we'll talk about other stars in the future. They're even bigger than this when they become super giants. But anyway, we have the hydrogen in the center. We've now become, sorry, we have the helium in the center. Let me write this down. We have a helium core in the center. Helium core in the center. We're fusing faster and faster and faster. We're now a red giant. The core is getting hotter and hotter and hotter until it gets to the temperature for ignition of helium. So until it gets to 100 million Kelvin. Remember, the ignition temperature for hydrogen was 10 million Kelvin. So now we're at 100 million Kelvin, factor of 10. And now, all of a sudden, in the core, you actually start to have helium fusion. Helium fusion. And we touched on this in the last video, but the helium is fusing into heavier elements. And some of those heavier elements, and predominantly, it will be carbon and oxygen. Carbon and oxygen. And you may suspect this is how heavier and heavier elements form in the universe. They form literally due to fusion in the core of stars, especially when we're talking about elements up to iron. But anyway, we have the core now is now experiencing helium fusion. It has a shell around it of helium that is not quite there, does not quite have the pressures and temperatures to fuse yet, so just regular helium. But then outside of that, we do have the pressures and temperatures for hydrogen to continue to fuse. So out here, you do have hydrogen fusion. You do have hydrogen fusion. And then outside over here, you just have the regular hydrogen plasma. So what just happened here? When you have helium fusion all of a sudden, now this is once again providing some type of energetic support, outward support for the core. So it's going to counteract the ever increasing contraction of the core as it gets more and more dense, because now we have energy going outward, energy pushing things outward. But at the same time, at the same time that is happening, more and more hydrogen in this layer is turning into helium, is fusing into helium. So it's making this inert part of the helium core even larger and larger, denser, and even larger and larger, and putting even more pressure on this inside part. And so what's actually going to happen within a few moments from, I guess, especially from a cosmological point of view, this helium fusion is going to be burning super, I shouldn't use igniting or fusing at a super hot level, but it's contained to do all of this pressure. But at some point, that pressure won't be able to contain it, and the core is going to explode. But it's not going to be one of these catastrophic explosions where the star is going to be destroyed. It's just going to release a lot of energy all of a sudden into the star. And that's called a helium flash. A helium flash. But once that happens, all of a sudden, then now the star is going to be more stable, and I use that I'll use that in quotes without writing it down, because red giants in general are already getting to be less stable than a main sequence star. But once that happens, you now will have a slightly larger volume. So it's not being contained in as small of a tight volume. That helium flash kind of took care of that. So now you have helium fusing into carbon and oxygen. And there's all sorts of other combinations of things. Obviously, there's many elements in between helium and carbon and oxygen, but these are the ones that dominate. And then outside of that, you have helium forming. You have helium that is not fusing. And then outside of that, you have your fusing hydrogen. You have over here, you have hydrogen fusing into helium. And then out here, in the rest of the radius of our super huge red giant, you just have your hydrogen plasma out here. Now, what's going to happen as the star ages? Well, if we fast forward this a bunch, and remember, as the star gets denser and denser in the core, and the reactions happen faster and faster in the core, it's expelling more and more energy outward. The star keeps growing, and the surface gets cooler and cooler. So if we fast forward a bunch, and this is what's going to happen to something the mass of our sun. If it's more massive, then at some point the core of carbon and oxygen is forming can start to fuse into even heavier elements. But in the case of the sun, it will never get to that 600 million Kelvin to actually fuse the carbon and the oxygen. And so eventually you will have a core of carbon and oxygen, or mainly carbon and oxygen, surrounded by fusing helium. surrounded by fusing helium, surrounded by non-fusing helium, surrounded by fusing hydrogen, surrounded by fusing hydrogen, which is surrounded by non-fusing hydrogen, or just a hydrogen plasma of the sun. But eventually, all of this fuel will run out. All of the hydrogen will run out in the stars. All of this hydrogen, all of this fusing hydrogen will run out. All of this fusing helium will run out. All of, or this is the all of this is the fusing hydrogen. This is the inert helium, which will run out. It'll be used in kind of this core being fused into the carbon and oxygen until you get to a point where you literally just have a really hot core of carbon and oxygen, and it's super dense. This whole time it'll be getting more and more dense as more heavier and heavier elements show up in the core. So it gets denser and denser and denser. But this super dense thing will not, in the case of the sun, and if it was a more massive star, it would get there. But in the case of the sun, it will not get hot enough for the carbon and the oxygen to form. So it really will just be this dense ball of carbon, super dense ball of carbon and oxygen. And all of the other material in the sun, remember, it was super energetic. It was releasing tons and tons of energy. The more that we progressed down this, the more energy was releasing outward, and the larger the radius of the star became. And the cooler the outside of the star became, until the outside just becomes this kind of cloud of this huge cloud of gas and around what once was the star. And in the center, so I could just draw it as this huge, this is now way far away from the star, much even bigger than the radius or the diameter of a red giant. And all we'll have left is a mass, a super dense mass of, I would call it inert carbon or oxygen. This is in the case of the sun. And at first, when it's hot, and it will be releasing radiation because it's so hot, we'll call this a white dwarf. This right here is called a white dwarf. And it'll cool down over many, 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 many years until it becomes, when it's no longer, when it's completely cooled down, lost all of its energy, it'll just be this super dense ball of carbon and oxygen, at which point we would call it a black dwarf. A black dwarf. And these are obviously very hard to observe because they're not emitting light, and they don't have kind of they don't have quite the mass of something like a black hole that isn't even emitting light, but you can see how it's affecting things around it. So that's what's going to happen to the sun. In the next few videos, we're going to talk about what would happen to things less massive than the sun, and what would happen to things more massive than the sun. Although I think you can imagine the more massive, the carbon, then there would be so much pressure on these things because you have so much mass around it that these would begin to fuse into heavier and heavier elements until we get to iron.